Hello and welcome back. My name is Frank Noe and I'm from FU Berlin, and these are my deep learning lectures. Today, recurrent neural networks. Recurrent neural networks are the method of choice if we want to work with sequential data where we have, for example, text, video streaming, audio streams, etc. So where we have sequences of data where we don't have necessarily a fixed or a previously known length. And we want to nevertheless work with sequences of different lengths in a dynamic fashion. Recurrent neural networks do this by doing parameter sharing in time or in sequence length. And today we will look at different RNN or recurrent neural network architectures and how they can be trained and used, as well as several examples. And in particular, we will study the long short time memory, which is probably the most famous and one of the most important RNN architectures today. What are recurrent neural networks? So in the previous classes, we have talked about what's here called one-to-one networks. So we had inputs and outputs of fixed size, some sort of fixed size input array, some sort of fixed size output array. Example, a convolutional neural network where you had an input array, an input image, and you predicted a class. For example, in MNIST, you predict 1 out of 10 classes given an input image of a digit. So fixed size input, fixed size output. Also in the last lecture where we have talked about WAMP-nets, where we took two time slices of a time series and then predicted a low-dimensional representation of the slow manifold. Still, there was an input size that was fixed, just 2 time slices of a certain array size, and also a fixed output size. So that's all one-to-one. Now, recurrent neural networks are supposed to deal with situations where we have an unknown length of input or output. So we have sequential data, for example, time series data, or some other sort of sequential data, such as texts, so sequences of words. And we don't want to predefine what is the size of an input or an output. So we could have one-to-many, where the input size is fixed, but the output size is variable. So for example, the input is an image, and we want to generate a text describing what is in the image. It could be many-to-one. So let's say we have a text as an input, and we want to classify it somehow. So we want to, for example, decide what is the sentiment of a tweet text. So is it happy, joyful, angry, defensive, whatever. It could be many-to-many. So let's say we want to translate a text from one language into another language, or many-to-many in sync versus out of sync. So this example here is out of sync. So that could be done in text translation, for example. We put a text in, we spend some time processing the text, and then we produce an output text in a different language. Many-to-many would be something where we want, for example, a simultaneous translation of a spoken text that is live, let's say. So we don't want to spend time on processing the text. We want to do the translation as soon as possible. So these are all examples of where a recurrent neural network could be used. So recurrent neural networks are specialized for processing a sequence of values. Let's call them x1 to x capital T. Capital T is not necessarily a fixed number that we know in advance. It's just formally here something to indicate the length of sequences that we are using in practice, or something like a maximum length. But in general, the sequences could have a wide range of lengths. Except for the variability in lengths, what we expect is that information that is relevant to process the input or to solve the learning task can be found at different places in the sequence, and we don't know in advance where to find them. So for example, let's consider these two sentences. I went to Chile in 2013, and in 2013 I went to Chile. Same meaning, and let's say we want to find the year the narrator went to Chile. So that's the machine learning problem here. So the answer is 2013, but we can find it in different places of the input in these two examples. So that means we cannot use something like traditionally fully connected neural networks, where the parameters are associated with fixed places or fixed positions in the input. We have to use some sort of parameter sharing, similar as in convolutional neural networks. And this is indeed quite related. So convolutional neural networks, for example, 1D convolutional neural networks in this example, are quite closely related to recurrent neural networks. In fact, we want some very similar behavior. So in convolutional neural networks, we had the situation that, for example, certain features of an image could appear in different places in the image, but they should be recognized nevertheless. A cat is a cat, no matter if it's in the top left or in the bottom right of the image. So therefore, we learn certain feature detectors once, and then we apply them in that case, in the case of convolutional kernels, we apply them irrespective of where we are in the image. We apply them in every pixel neighborhood. And basically, we want to do something very similar here. So we want to share the rules that we use to recognize certain features across the sequence. Okay, so let's look at a simple example of a recurrent neural network, or RNN. And let's also look what RNN unfolding is. That is a very important concept we will be needing. So the example is this. Consider this equation, which defines a dynamical system in the signal x of t. So x of t is our time series or sequence that we are interested in modeling somehow. For example, we want to train a network to predict future states from past states. So we want to do time series prediction. And let's say our learning model, or the model that we use in order to model the evolution of x is as follows. So we have a variable h, which encodes our collected knowledge of present and past. So it's some sort of hidden variable, which is some summary statistics, if you like. It's also a time series, so it depends on t. H of t is updated by using the function f, which depends on ht minus 1. So that is the recurrent part. So it depends on the last time step and on the current time step of x. And it depends on the parameters theta. So the parameters are trainable. So f is a trainable function, a neural network function. Okay. So this is, you can think of the function f compressing information from the present and past into h. In general, this is a lossy compression because our variable h has finite size, but our time series can have arbitrarily long size, so can be arbitrarily large. So that means at some point our function f will do a lossy compression if the time series becomes so long that we cannot completely record it in h anymore. Let's look at these two graphs here. These two graphs are graphical representation of the function up here. So on the left side, we see a compact representation, which is exactly like the equation itself. It's a recurrent representation. So h of t is updated by function f as a function of x of t and ht minus 1. And we encode the t minus 1 with this bullet. So the bullet is a time delay of 1 step. Now we can also unfold this compact graph into this graph, which explicitly lists different time steps. And we do that here for time steps t minus 1 to t plus 1. So we have to start with an initial value of h. So let's say ht minus 2, or let's say h0, some initial h value, so that we can start the recursion. And then we update h of t minus 1 by applying f to this initial value of h and h of t minus 1. So now we have computed h of t minus 1. Now we can apply f again to compute h of t using h of t minus 1 and x of t. And we can do the same for h of t plus 1, etc., etc. So in this way, we can unfold the sequence or the recurrent neural network into an explicit time sequence for as many time steps as we want. So in other words, an unfolding or folding of a recurrent neural network switches between this recursive definition that we had up there, f of h t minus 1 xt, and a feed-forward representation that we here call g of t. So what you see on the right, in the right-hand side of this graph, is a feed-forward neural network which represents the last hidden variable h as a function of the entire time sequence x1 to xt. Okay, every recurrent neural network defined in this way, f of ht minus 1 xt, can be unfolded into a feed-forward neural network of the time sequence x. But vice versa, this is not true. You cannot fold every feed-forward neural network that depends on an entire time sequence into a recurrent neural network. And the reason for that is the recurrent neural network has this particular parameter sharing structure, so that every time step can be computed from the last hidden variable, the hidden variable at the last time step and the current observation, using the same parameter set. Right? So this is the parameter sharing structure here. So folding and unfolding of neural networks, that's a very important concept. Keep that in mind. Okay, so let's look at a more interesting recurrent neural network structure. This is a basic universal recurrent neural network. Let's see what that is. So first of all, the structure is as follows. We have a time sequence x of t again. And now we have again a hidden variable h of t, such as in the last example, which is some sort of summary statistics of our observations of present and past. And we additionally have now an output signal O of t. This is the core of our recurrent neural network. It depends on parameters u, v, and w, and some functions that use these parameters and the corresponding inputs to update the functions h and o. That's the core. Then we additionally have a time series y and a function L. Now this is made for supervised learning. So y is basically meant to be some sort of reference output that we expect, so labels that we train the neural network to reproduce, and L is representing the loss function, which measures the distance between the y and the O series. So the most important part of the recurrent neural network is this x, h, and o, and the respective functions which compute them. Now, the interesting thing about this neural network structure, this recurrent neural network structure, is that it's a basic universal RNN. So that means with a finite size, so a finite time step length, you can compute any function that is computable by a Turing machine. So basically, this RNN can learn any algorithm. So that's an interesting analogy to our universal approximation theorem of feed-forward neural networks. So there we had universal feed-forward neural networks, or universal function approximators. Those were feed-forward neural networks with two layers, so a hidden and an output layer, and a sufficiently large number of hidden neurons. So with such a feed-forward neural network, we could represent any smooth function on a compact set, right? So that's the function representation theorem, using universal representation theorem. So here we have the corresponding thing for algorithms. With such a two-layer recurrent neural network, if we have enough time steps available, we can approximate any function computable by Turing machine or any algorithm. Let's go one step more concrete or specific and look at one implementation of the structure. So here we can use the update equation as follows. So we update the hidden variable h of t using a linear function of h of t minus 1 and x of t. So the coefficients or the matrices that we use in this linear function are w and u. So those are parameters. And additionally, we have the parameter vector b, that's a bias vector. Then we put everything through a nonlinearity, in this case, a hyperbolic tangent function. So that's our update for h. Then we have an update for the output sequence. So here we assume that the output sequence is a sequence of classes, so a classification. And therefore we use the softmax function. The softmax function takes again a linear transformation of h of t. So we have matrix V to transform h of t, and we have a bias vector C. The softmax function is defined here. We have used it before, but I think we haven't explicitly defined it on a slide. So basically we take for every output neural network, so for every neural network in the layer that we use the softmax on, we take the exponential of the activation and we divide by the sum of exponentials of all activations. So that has two effects. So first of all, the outputs of the softmax are always between 0 and 1, so they're always non-negative, and they always sum up to 1. So they represent a fuzzy classification or clustering. So that's good for classification. Okay, so this is an example of how we can implement such a universal recurrent neural network. Very simple implementation. And we have the following parameters. We have the bias vectors B and C and the weight matrices U, V, and W. So how do we train such a RNN? So first of all, we need a loss function. Here we use supervised learning. So we are predicting a time series O, and we have a label time series Y, and we want to minimize the difference. So a simple choice would be mean square error of O and Y. Another choice is a probabilistic error. So if O represents a time series of classifications, so class probabilities over time, as we got with the softmax function that we've used in the last slide, and Y just represents a reference sequence of classes, for example, in a one-hot encoding, we can also compute a probability. So for every time step, we can compute the probability of observing the class that we want to observe, Y of t, given the class probabilities predicted by O of t. And then we can take the products of these probabilities along time, and we can take the logarithm of the product, and then we have a log likelihood of making the observation sequence Y given the predicted class probability sequence O. So that's one thing that is often done. But irrespective of what exactly we use here, we have some sort of loss function that compares O and Y, and that we can minimize in order to train the parameters of the neural network. Now, how is training done in practice? So first of all, we have to unfold the neural network. So we go from the top left representation to the top right representation, and we unfold the neural network into capital T steps. We then take mini batches in time. So we take sub-trajectories of X and Y this is basically our training set. We have trajectories x and y. Maybe you have one long trajectory, x of t and y of t, or we have several trajectories, x of t and y of t, of different lengths, and we subsample sub-trajectories of length capital T. And then we use them on this unfolded neural network that has been unfolded for capital T time steps. And then we train it like a normal feed-forward neural network. So we have an input sequence of capital T steps. We have a label sequence of capital T steps. We compute an output sequence or predict an output sequence O of t with capital T time steps. Use the loss function to compare y and o. Take the derivative of the loss function with respect to the parameters u, v, w, etc. and update the parameters using backpropagation. So this is normal backpropagation, and we call it backpropagation through time because we are applying it on a recurrent neural network that has been unfolded in time. This unfolding has the effect that the same parameter set appears at multiple time steps, because that's basically the parameter sharing in time. So for example, the u parameter appears 3 times in this picture in the top right. But that's the same as in convolutional neural network, where the parameter set appears around every pixel that we are training. So that's nothing new. And so the disadvantage of doing this is that training becomes quite expensive. So our runtime is now linear in the number of time steps capital T, so in the sequence lengths of the subtrajectories that we train for. And we cannot parallelize over time steps, so we cannot compute them independently because of this dependence in time. So h of t can only be computed once we have h of t minus 1. H of t plus 1 can only be computed once we have h of t. So there's certain sequentiality here in the graph. We cannot parallelize most of the computations. So every single mini batch computation can become quite expensive, computationally expensive.